Hello, my name is Sam and you are watching Wiley Maths. This is a A-level further maths video about differential equations. This is specifically first order differential equations. I will cover second order differential equations in a separate video, but this is just first order differential equations. So what is a differential equation? Well, we've got one up on the screen. dy by dx equals 2x, quite possibly one of the simplest differential equations you could write. A differential equation is any equation that includes a derivative or a rate of change of something with respect to something else. Could be dy dx, could be dx dt, could be dz dq for whatever reason. But it's any equation which includes a derivative such as that, and also other variables. So this is dy by dx is equal to 2x. And in this case, you want to try to solve this differential equation or find a general solution. So we do not have any information about any values of y, x or dy by dx at any given circumstance, and so we cannot find a particular solution for this differential equation. Instead, we are going to calculate a general solution for this equation. So if you are experienced with some simple calculus up until this point, you may think, well, why don't we just integrate both sides? Effectively, integrating both sides will give you y is equal to x squared plus c. And that is technically correct, but you need to write down the method. And that is not the correct method, unfortunately. The way that we're going to do this is we're going to collect, much like Year 7 maths, we're going to collect our like terms. In fact, we're going to collect all of the variables on one side of the equation and all of the variables on another side of the equation. In order to do this, we have to break some rules of maths, and we have to treat this derivative like it is a fraction. That is not what it is in real life. D by dx, or d by d of any variable, is considered an operator, but the reason why it's represented as a variable is because it can behave in such a way, and we are going to use that behavior now. So what we're essentially going to do is we're going to multiply our equation on both sides by dx, but if we're going to do that, we have to also integrate both sides at the same time. So I'm going to do dy is equal to 2x dx, that's my multiplication, but I have to integrate both sides at the same time. This is an integration of 1 dy, and this is an integration of 2x dx. An integration of 1 dy is just equal to y, and an integration of 2x dx is equal to x squared. We do need a constant somewhere on this equation, so I'm going to add plus c somewhere here on the equation. It doesn't matter which side plus c is on, as it's a constant. You also do not need to include two constants, as both constants can be any number, they are constants, and so you can just put them on one side of the equation as one value. And that is what's known as the general solution for dy by dx is equal to 2x. A particular solution would be a result that tells you a value of y, it can tell you a value of x, it will tell you the value of c for any given system with a known value of y, x, or dy by dx. You could say that y or x are some starting variables in a system, and dy by dx is the rate of change of those variables. And therefore, you could calculate c if you knew the initial variables y and x. So let's move on to a harder example. So this one looks a little bit different. We're still going to use the same method for solving our first order differential equation. This is a first order equation because the derivative is just a first order. It is not a second derivative, it is a first order derivative. And so in order to solve this, we will use the same method. We need to manage to get all of the variables of one type on one side of the equation and the others on another side of the equation. So if I write out the equation, we can try and see which side each variable is going to go on. Well, dy is on the top of this fraction, so I would like to move the y onto the other side of the equation and multiply up by dx. So I'm going to have 1 over y dy by dx equals 2 over x. And then we can do the trick which we did in the previous example. We can multiply both sides of the equation by dx and integrate at the same time. So the integral of 1 over y dy is equal to the integral of 2 over x dx. What is the integral of 1 over y? Well, what's the derivative of y? It's 1. So the integral of 1 over y is ln of y, or the natural log of y. The integral of x dx, well, what's the derivative of x? It's 1. We want 2 of those, so this is going to be 2 ln x. And then we need to add our constant on as well. And so far, that is the answer to this, well, that's the general solution for this differential equation as well. So let's move on to a harder example. Now this one looks a little bit different. We have a 3x multiplied by our dy by our dx plus y, and that is going to equal x. Unfortunately, this is not in the same form as in the previous example. We have two different terms of x, they are not on the same side of the equation, and we cannot get all of them on one side of the equation. If we divide by x, we're going to have a y over x. Unfortunately, things just aren't going to work out if we do that, so we need another method. This is where the integrating factor comes in. So there are two ways of using the integrating factor. So our aim is to use the product rule to solve this. So the product rule is when you differentiate two terms, your answer is going to be the differential of your first term times by your second term plus the differential, that looks like an A, the differential of your second term times by your first term. We're going to want to try and get something similar to this to appear in this equation here. Unfortunately, it is not already in that format, and so we need to make it in that format. And this is where you use the integrating factor. So the integrating factor is something that you multiply both sides of the equation by, or well, the whole equation by, in order to make it so that you are able to perform this operation. Well, you're not performing this operation, you're doing it backwards. You need to recognize when you see the product rule come into place, and you need to be able to work backwards from that to get a differential of a single term is equal to another term, in which case you can integrate both sides, much like we've done in the previous examples. So how does the integrating factor work? Well, I'm going to show you the method here. There is a proof for this, but the proof is rather long and you do not need to include it in an exam answer. You do need to include all of your full workings, of course. You need to show that you're using the integrating factor. You need to show what your factor is going to be and all of that, but you do not need to show that the proof. So I'm going to divide both sides of the equation by 3 here. Sorry, I'm also going to divide both sides of the equation by 3x. That means I need to remove the whole equation. So we're going to have dy by dx plus y over 3x is equal to x over 3x, which is 1 over 3. And again, we can see that we can't subtract any of these y over 3x values and collect everything on one side of the equation, so we're going to have to use our integrating factor. Now, if I rewrite this in a different form, well, it's not necessarily in different form, but if I rewrite this as 1 over 3x times by y equals 1 over 3, we're going to have something going on here with our coefficient of our dy by dx and our coefficient of y, which is going to be able to make us use this product rule. The y is already in the right format, as the differential of y is dy by dx, but I definitely know that this is a 1, and the differential of 1 is not 1 over 3x. So in order to find the integrating factor, you need to perform e to the integral of this term here, your prefix to this function of y. So this is 1 over 3x, so it's going to be integral of 1 over 3x dx. That is your integrating factor. The result which you get from that, usually you're going to be using a fraction, so you will get a ln. That is going to be what you will multiply the whole equation by, and we're going to see where this goes in a minute. So the integral of 1 over 3x dx, well, the derivative of 3x is 3. We want a third of that, so it's going to be e to the third ln x. And a third ln x, I can move the third up as a power up here, so I could make it minus 3. Or I could make it, sorry, not minus 3, I could make it a third, just go up on the x power there. The e's and the ln's will cancel, this gives us x to the power of a third. That is our integrating factor. I'm now going to multiply the whole equation by this integrating factor. So I'm going to have x to the third, that's dx, x to the third dy by dx, plus Now I'm going to multiply this again by x to the third, but usually it helps you to cancel whatever you've had. X to the third over 3x y is equal to x to the third over 3. Now this looks complicated and annoying, but actually you don't need to worry about that, because the way that the product rule works is you have the differential of your first term times by your normal term, and then your differential of your normal term multiplied by your first term. So if this is a differential of y, then we know that this is our value, this is one of our starting values. And we also know that y is one of our starting values. There's a blue square. I can't get rid of it. So we can say that our new equation is the differential with respect to x, so d by dx, that's the operator for differential, of x to the third, that doesn't look like 3, x to the third y, and that's going to be equal to x to the third over 3. Now we can integrate on both sides. This is d by dx. If we integrate both sides in terms of x, then we can remove this differential operator, and we can have x to the third of y is equal to the integral of a third x to the power of a third dx. I'm sure you're all very experienced with doing integration like this, but the answer to this integral, x to the third y is equal to, you add the power by 1, so it's going to come 4/3, divide by 4/3 is times in by 3 over 4, a third times by 3 over 4 is 1 over 4, so this is going to be a quarter x to the 4/3 plus c. This plus c is very, very important. In this case it is not so important, as we are not trying to find a particular solution, but in terms of the general solution, that c is very important. And so if we're going to express y in terms of x, we can divide through by x to the third, so we get a quarter x to the, and then 4/3 minus 1/3 is, well, x to the 3 over 3, which is x to the 1, plus c over x to the 1/3, or x to the minus 1/3. And that is your equation for y written in terms of x, also known as your general solution. So let's move on to another question. Now this one, again, unfortunately, fortunately, this one does not need the integrating factor. So this is the other case. I think these questions were meant to be the other way around in this video, but yes, this is the other way around, in which case you can use the product rule backwards, but you do not need to use the integrating factor. So x dy by dx plus y is equal to cosine of x. Now we can see here that this is the application of the product rule. We have x times by the differential of y plus the differential of x, which is 1 with respect to x, times by y. And that's going to be equal to cosine of x. Now I can simplify this straight away to be d by dx of x, y, and this is going to be equal to cosine of x. If I integrate both sides, then we get xy is equal to the integral of cosine of x with respect to x. So xy is equal to the integral of cosine of x is sine. Sine differentiates to cos integrates into sine. So this is sine of x, and this is plus c. So our equation for y in terms of x is 1 over x sine x plus 1 over x of c. Again, if you knew your values of y and x, or your differential of y, then you could calculate the particular solution in that case. So we can see that this is a much easier option when you think about the amount of effort that you've gone through in order to solve this. However, a question like this would obviously be much less marks than the previous question, which used the integrating factor. But as you get used to it, the integrating factor is not necessarily too tricky of a thing to work out. So let's work out a particular solution question. This is the last example that I have, and this is where we're going to calculate a equation for y in terms of x, when y is equal to 1 and x is equal to 1. This is also known as a particular solution. In this case, we are going to get a value for c. So after we have done our integrating factor, if we need it, and after we have calculated the integral of that solution, and we found y in terms of something, We will input values of 1 for y and 1 for x. We will find our value of c and rewrite our equation just in terms of y and x. That is known as a particular solution. So let's get started. We have x cubed dy by dx minus x squared y equals 1. Now we can see that if x cubed is going to be our x term, the differential of x cubed is 3x squared. Unfortunately, we only have a minus 1x squared. So this is not in the format where we can avoid the integrating factor. Unfortunately, we have to go ahead and use it. So in order to use the integrating factor, we need to have just the dy by dx. We're going to divide by this x cubed. So x squared divided by x cubed is just 1 over x. This is times by y is equal to 1 over x cubed. I'll rewrite that in the next equation as x to the minus 3, but just for now, it's 1 over x cubed. So our integrating factor is going to be e to the integral of minus 1 over x dx. And to calculate this, the derivative of x is 1, so this is going to be e to the minus ln of x dx. This minus can come up, so this is an x to the minus 1. The e and the ln cancel, so this is just going to be x to the minus 1 is our integrating factor. We got lucky there that e and the ln has cancelled. Sometimes when you don't use a fraction as your integrating factor, you do get e values, and those can be some really hard, really meaty questions. But in this case, we haven't had to do that. So let's multiply our equation by our x to the minus 1, or our 1 over x. So here we have 1 over x dy by dx minus 1 over x times by 1 over x is 1 over x squared y is equal to 1 over x cubed. We're going to use 1 over x and y as our derivative value, so d by dx of 1 over x times by y is equal to, I didn't multiply this by 1 over x, so this is going to become 1 over x to the 4. This is equal to 1 over x to the 4, and then we need to integrate both sides. So we get 1 over x times by y is equal to the integral of x to the minus 4 dx. Add 1 to the power makes it minus 3. Divide by the power is minus a third x. So we get 1 over x y is equal to minus a third x to the minus 3 plus c. Now the plus c is going to become a value, but unfortunately before we get that far, we need to finish getting our expression for y. So if we multiply the equation by x, we're going to get minus a third x to the minus 2 plus cx. Now we can substitute our values of y being 1 and x being 1 to see what our c value is going to be. So our y value of 1 is equal to minus a third of 1 to the minus 2 plus c times by 1. Now 1 to any of this power is just going to be 1, so 1 is equal to minus a third plus c. C is equal to 1 plus a third. 1 plus a third is going to be 4 thirds. C is equal to 4 thirds. Therefore, we can confidently say y is equal to minus a third x to the minus 2 plus 4 thirds x. And that is our particular solution for y being 1 when x is equal to 1. This is also not the general solution, so you wouldn't be able to say this is a general solution, but is a particular solution and is the answer to our question. You can write that with the 1 over 3x squared if you so wish, but yes, x to the minus 2 is how I like to write it. That's all I have for today. Thank you for watching. Do subscribe if you enjoyed the video. Comment down below if there's something you want me to have a look at, and thank you once again.